Good morning, dear students. Welcome back. Starting the new semester of advanced calculus, and it will start from integration. Integration calculus of functions of one variable. Let me share my screen. Today we will study basic methods of integration. So we will use table of integrals, uh, differential entry technique, and integration by parts. So now let's start with uh, just using uh, integrals properties and table of integrals. So the first task. So let's calculate the following integral. Let me move this panel. Mhm. So square root of x plus 1. So actually what we see, it is a power function. So we know how to integrate it. So what do we have to do? Let me first of all expand the brackets, and then it will be more understandable how to calculate it. So uh, x by square root of x minus x plus square root of x. So multiplied square root of x by this. And now I just will add this. Now let's simplify. So square root of x can be eliminated. X can be eliminated as well. So we just have a sum of these functions. So now we can use the table of integrals. Uh, so you always can see it maybe in lectures. Yeah, good morning, Bogdan. Uh, so uh, Actually, let me remind you that antiderivative, a definite indefinite integral from uh, x in power of alpha uh, equals the following: 1 by divided by alpha plus 1, and x will be in power of alpha plus 1, and don't forget about the constant. So uh, what do we have here? So x in power over 3 by 2. So if we add 1, it will be power of 5 by 2. So we divide by it, so 2 by 5. And here we just increase the power. And here is power of 0, so plus x, and don't lose constant c. It actually will be useful when solving differential equations. It will have more usage. So if we differentiate, we'll receive this expression. Of course, it can be factorized. Any questions about this task? Okay, I guess that no questions. Actually, part B is done analogically, so we divide both these addends by square root of x and integrate like this function, power function. So let's skip it and let we better uh, solve part C. So it's more interesting integral. So it looks not so easy, but uh, cosine of 2x, cosine of x and sine square of 2x. Yeah, and also don't lose dx and the integral. It will be important for us soon. Okay, so how to solve it? Any ideas, suggestions? How can we uh, calculate such integral? So this expression looks complicated, but it can be simplified. No idea? Okay. So uh, we need to transform this expression. So let's remember some trigonometric functions. So cosine of 2x can be written in the following way: cosine square of x minus sine square of x. And uh, let's remember some properties of integrals like linearity. Uh, so we can write it like this. So like a difference of two integrals. So what do we have now? And can we do next? So we can just, so for first integral, cancel cosine square of x, and for the second sine square of x, not 2, but everywhere 1. Yeah, so that's maybe you were confused about what to do. So it was a mistake. So it looks like this. And now we have two table integrals. So these integrals, so if we integrate this function, we will receive minus cotangents of x. And this integral, so if we calculate this integral, we will receive tangents of x. And this is the final answer. Any questions about this task?
No questions.
Okay, no questions. Now let's move to part D. Here we will have to use differential entry technique. So, how does it work? So, let me first write down the integral to x minus 3 in power of 5. So, we actually don't have such integral in the table, so we know that we know integral like so we know how to calculate this integral. But how to calculate this integral, it's a question. So we actually need to transform this initial integral to this form to be a table integral. So how can we do it? Now we will use the differential entry technique. So we are interested to move under differential this expression. So so differential of this expression is the following. So it just 2 dx. So we differentiate it. And so what can we do here? So we need to transform this expression to such form. And by the way, if I differentiated this expression, I will receive 2dx. So we have not to break equality. So it will be 1/2 of this differential. So if I differentiate it will receive this integral. But what we actually have an integral that looks like this. I also can make even a substitution like 2x minus 3 equals t. So I can replace it with t, and it will be the table integral. But for such simple examples, for such simple tasks, we don't really need to do it. So we will receive, so this is power of -5, and in antiderivative we will have power over -4, and so divide by -4. So it equals -1/8 divided by 1 by t in power of 4. And if we return to old variables, so we can use this expression. Yeah, and plus constant c. Don't forget about it. So any questions about this task? I guess there are no questions. Okay. Part E is analogical approach. Now let's solve F. And so we have the next integral. So which integral do we have to receive? So how to calculate it? We know such table integral. So dx divided by x. So in power of 2 plus a in power of 2. And it equals 1 divided by a, and arctangents of x divided by a plus c. So we need to transform initial integral to this one. So again, differential entry technique. So here we have this, and here differential of 2x. So everything is okay here. Actually, by the way, what table of integrals do you have? So do you have their function, maybe function u that is a composite function, or just x? So which do you have in lectures?
You.
Okay, so like so we can understand it as a composite function, so not like a usual variable. And here u equals 2x. So and here square over 2x. So now we can integrate. But let we do it from the next line. So 1 divided by square root of 3, because it is a square. And this is arctangents over 2x divided by square root of 3 plus c. Any questions about this task?
Yeah, I have a question.
Yeah.
Why do we have differential of 2x, 2x?
Uh, so because of such integral. So u equals 2x. And u square equals 4x in power of 2. So we need to use a differential entry technique.
Oh yeah, I see that. Thank you.
You are welcome. Okay, more questions? Okay, if no questions, let's move to the next task. So other examples. So of course it will be better if you calculate in your own, but you also can check yourself here. And now, so we will use the differential entry technique for these integrals or substitution method. I don't think that substitution method, so that we will really need it, but let's see. So for a, so let's calculate integral a. So any ideas how to solve? So any steps how to start calculating? No? Okay. So actually you need just to so more practice to see the differential. So what can be moved under the differential? So here we can move. So here I see differential of tangents. So it equals dx by cosine square of x. So we have a differential of tangents. And what we will receive now? So now we just have a kind of power function. Yeah, let me make some small spaces, just not to get confused. So now this is a power function, 1 by 4, and we have tangents over power of 4 of x plus c. Any questions about this task? Okay, I guess no questions. So now let's move next. So let's solve the next integral. So x by dx and divided by x square of say x in power of 2 plus 1. So what can be moved under the differential? So your ideas. Still no idea? Okay, let me help you. So we have the differential of x in x squared plus 1. So well, how can we receive x? We can differentiate x squared divided by 2. But we have here this expression. So differential of this expression will be equal to x dx. And uh, how to calculate this? So how to transform this? So x dx will be equal 1 second of this, so half of this differential. So now let's just let's use differential entry technique. Let me move to the next line. So I have this, and we have just a power function. So this is x. So this is u in power of minus 1 second, and the antiderivative will be 2 u in power of 1 second. So 1 second multiplied by 2 these square roots plus c. And I can just cancel fractions, I can simplify, and what will I receive? Any questions about this task?
Why we write 1 second? Just didn't understand it.
Here?
Yep.
Well, we don't have to break the equality. So if I differentiate this expression, I will receive 2x by dx, and it will not equal to this integral. And we need to divide by 1 second not to break equality. So
Understand, thank you.
Okay, and now let's move next. So integral c. So we will use, so it's an interesting integral, so we will use different properties of integral. So what will be the first? So what can we see here? So your ideas, how to solve? So if I differentiate this expression, I will receive minus 2x dx. And what do you think? So only differential entry technique will be useful here, or we need to use some other approaches beside differential entry. Okay. So now let's use a property of linearity of the integral. So we will make a sum of integrals. So we will transform it to sum of two integrals like this. So the first one is the table integral. And it actually equals arc sine of x plus c. So this is a table integral. And this can be calculated with the differential entry technique. So now let's calculate the next. So arc sine of x, so constant c will be added in the final answer. Okay, so by the way, first of all, let we find the differential of this expression. So differential of 1 minus x squared equals minus 2x dx. And this expression will be equal minus 1 second of this. So again, not to break the equality. So now what we will receive minus 1 second. So this integral will be the next. Look like this. So x arc sine of x remains. And minus, so we will receive 2. So minus this square root of 1 minus x squared plus c. So any questions about this task? So sometimes you have to combine properties of integrals with different approaches. Okay, if no questions, let's move to part C.
Wait, excuse
Yeah.
me. You have after arcsinus x, you have plus, but but in the next you have a minus in,
Yeah,
in the next line.
thanks for your attention.
Thanks.
Yeah. Okay, let's move next to D. So don't need it for now. So power of 2, 1 plus x square and dx. So what can be used, so what can be moved under differential? So your suggestions. I guess you already, you start seeing it. What can we transform? Yes, Sophia?
I guess arctangent.
Are you sure? Oh, so you mean
I mean the whole like
yeah,
arctangent
so
x.
differential of arctangents. Yeah.
Yeah.
Yeah, correct. So we can do like this. So yeah, our integral is transformed, and again we have a power function. So it will be 1/3 of arctangents x in power of 3 plus c. So quite simple. So looks, so it doesn't. It's not such complicated like it looks from the first view. And now the next integral. So dx by cosine square of x and multiplied by this expression. So what can be moved under differential? Who else can suggest something? How to simplify this expression? So which differential do you see of which function here? So no ideas. So we can receive it if we so 1 divided by cosine square of x can be received if we differentiate tangents of x. And if we differentiate such expression, we will receive it as well, because 1 will be 0 after differentiation. So differential of this expression equals dx by cosine square of x. So now let's simplify this integral. So power function. So we have 2 square roots of 1 plus tangents x plus c. Any questions about this task?
No questions.
Okay, no questions. So now let's solve one more example. So f and now I'm here. I'm open for your suggestions, comments, how to simplify this integral. So what can be moved under differential? Okay, so maybe anybody else wants to participate in discussion. So I want everyone to be involved. Okay, I see that everyone are so shy. So Sophia, go on.
I guess we can find the differential of ln x.
Yeah, so actually here we have a differential of a logarithm. So correct. So this is dx by x. So after some small transformations, we receive such integral. And what we will have, so the antiderivative of logarithm, so let me remind you, no, antiderivative of this, du by u. So it equals logarithm of module u plus c. So be attentive, don't lose modules. Any questions?
I suppose not.
Okay, if no questions, let's move to the next task, and yeah, let's see how many tasks do we have. Okay, so the next integrals will be calculated uh, uh, with integration by parts, but I suggest going for a break for 5 minutes and then just move to other logical point. So maybe if you have some questions, if just appeared in 1 minute, so I will answer them. If not, so everything after the break. Okay, so we'll continue in 5 minutes, after 5 minutes. Okay, let's continue. Okay, let's continue. Let me share my screen. Just a moment, something went wrong. Okay, so now let me remind you integration by parts technique. So here is the formula of integration by parts. Actually, we will use a kind of differential entry technique for that. So it looks like this. So we have initial integral where function v is under differential, and then we receive the next. So functions u and v. So functions u and v minus integral of v, where u is under differential. So the main question is to define which of functions must be defined as u and which of them as v. So we see here different like products of functions. So what actually must be what? So if we have a product of polynomial and exponent, polynomial of cosine or sine, so we choose u as a polynomial and dv as a trigonometric or exponential function. For integrals like this, polynomial multiplied by logarithm, arcsine, arccosine, arctangents or arccotangents. So we choose p. So the polynomial is dv. So polynomial is v, and arctangents. So other functions are chosen as u. And also we have integrals where for which it doesn't matter which to choose. So composition of cosine and so cosines are duplicated. So composite functions of sine, cosine, and logarithm. So it doesn't. Oh yeah. So it's better to choose u as hold this function and dv as dx. For such integrals, so they are called recurrence integrals. You will understand why are they called in such way. So it doesn't matter which part is v and which is u. So any questions about this guide? Okay, now let's start solving exercises, and questions will appear. So where are they? So we have the next integral. So x multiplied by sine of 2x and dx. So according to our rules, so u equals x. By the way, let's do like this. And du equals dx. So now dv. So dv equals sine of 2x by dx. And so v equals, so we need to just to integrate this expression. So v equals minus 1 second multiplied by cosine of 2x. So we have everything to integrate by parts. So we multiplied first of all u and v, so it's better so to do like this. And then minus integral over v by du. So we will have plus because of minus here. And of course, let's move 1 second out of from integral. So cosine of 2x, and so v is done. And what about du? Du equals just dx. So what we will receive? So 1 second x, so minus 1 second x by cosine of 2x, and plus, so antiderivative of this function will be 1 second sine of 2x. So plus 1/4 sine over 2x plus c. And this is the final result. Any questions about this task? Okay, I guess that no questions. So let's move next to part B. So we have, yeah, by the way, let we do it a little bit complicated, so more interesting. So let we multiply by x in power of 2. So multiplied by e in power of minus x. So for this, we will have to use integration by parts twice. So it depends on power of the polynomial. So just to make it more interesting, we actually have time for that. So now what we have, u equals x in power of 2. So du equals 2x dx. And so dv equals e in power of minus x dx. And v equals minus e in power of minus x. So what do we have? So u multiplied by v, so minus x in power of 2, e in power of minus x. Plus, so because we have minus here, plus integral of, so let's move to out of brackets, 2, so x multiplied by e in power of minus x dx. So, and again, we need to use to apply integration by parts. And now we have, so u equals x, so du equals dx. For dv, nothing changes because it is the exponent. So, continuing calculation, so plus 2, and this will be in brackets. So, minus x multiplied by e in power of minus x plus e in power of minus x dx. So uv is here, and so v and du. And now let's integrate once more. and plus c. So that's it. Any questions about this task? So just for your understanding how to integrate by parts, we have power of polynomial higher than 1. Okay, if no questions, let's continue. Huh?
I may have one question. So
Sure.
does this mean that the number of times we have to repeat do the procedure entirely depends on the power of the polynomial or not, or of the u, that is?
Well, so for integrals that looks like this, so polynomial multiplied by exponent or cosine or sine, yeah, so it depends on the power of polynomial. So have I answered your question?
I suppose so. So if it was a power of 3, we would have to pretty much do the procedure both. We would have to do it 3 times instead
Yes,
of yeah.
correct.
Okay.
Yeah, so I just decided to increase the power just to show you
All right.
more
Thanks.
interesting example. Okay.
Those make sense. Yeah.
Oh, maybe more questions, and I raised it so earlier that needed. Okay, so I guess that no questions, so let's move next. Now we have the following integral. So just a second, let me plug in my laptop. Okay. So arc sine of x and divided by square root of x plus 1. So actually we have not a polynomial here, but again we will use integration by parts. So what is what here? So u will be, so u is arc sine of x and du, stop. Okay. So du equals dx multiplied by misclick 1 minus x in power of 2. And dv equals dx divided by square root of x plus 1. And v equals 2 square root of x plus 1. So now let's integrate by parts. So 2 square roots of x plus 1 multiplied by arc sine of x and minus the following integral let me put to here. So what we received, we actually can so now we can do some manipulations with this integral, so transform it a little bit. So we can use the following. So what do we have here? This is the difference of squares. So, and if we even write it, so if I even expand it more, so it looks like this. So we can cancel square root of 1 plus x. And what do we have here? So we will use the differential entry technique. So I will write plus here, and here we have differential of 1 minus x. So the final answer will be the following. So 2 square root of x plus 1 multiplied by arcsine of x plus 4 square roots of 1 minus x plus c. So any questions about this task? Okay, I guess that no questions. So now let's move to exercise D. So integral, so the following integral of our cosine. So what is what here? So so arc cosine of, so u equals arc cosine of x, and du equals, don't forget, so be attentive with the signs, so minus dx divided by 1 minus x square, and dv equals dx, and v equals x. So now calculating the integral. So integrating by parts. Plus this, so because of minus here, so we will receive the next integral that can be calculated with using differential entry technique. So minus 1 second and the differential over this expression. So now let's integrate it. So minus minus this square root. So because we will receive so minus 1 second multiplied by, okay, let me write in details, multiplied by 2 square roots of this. So because of power of 1 second, and we divide by power. And now let's cancel these numbers. So it's done. Any questions about this exercise? Okay, I guess that no questions, so moving next. So the next integral, so as I told you before, so it is so exponent multiplying by sine. So it is a recurrence integral, and it doesn't matter what will be used as u, what will be chosen as u, what is as dv. Okay, what we use, so u like exponent will be u. So du equals e in power of x dx. By the way, recurrence integrals must always must be calculated, so taken by parts twice. You will see why. Dv equals sine of x dx, and v equals minus cosine of x. By the way, when integrated by parts, so not only when integrated by parts, always will be, please be attentive with the signs. Yeah, because it's easy to lose the sign. So plus the following integral. So e in power of x cosine of x dx. So again, we need to use integration by parts. So by the way, if firstly you took u as the exponent, it will be okay. What I mean. So if you take when first time taken by parts, if you take u as the exponent and v as a trigonometric function, so you need to do it in the second calculation as well. So you mustn't change them. Otherwise, you will only make your calculations more complicated. So more actions. So again, u equals e in power of x and du equals e in power of x dx. So dv is now is cosine of x and v equals sine of x. So this function and plus, so uv e in power of x by sine of x minus, so now let's move u, v and du under the integral. So e in power of x sine of x dx. And I have a question. What do you see now? Interesting. So look attentively at this
Well,
integral.
yeah, we have received the integral that was the like original one.
Yes, that's why it's called recurrence integral. So we now just for easy understanding mark integral like this. So, and we will receive the following equation. So I equals this minus I. So we need to calculate, so we need to solve this equation relative to, so with respect to I. So 2I equals this. And finally, I equals, so 1/2 of this expression plus C. So that's why recurrence integrals must always must be always calculated by parts twice. So any questions about this task? Okay, as I guess no questions. Okay, so let's solve the last exercise for now. So the last integral. Yeah, it's definitely the last. So again, this is the recurrence integral. So sine over logarithm x dx. So for our for more convenience, let we take u as this expression. So du equals 1 by x multiplied by cosine of logarithm x dx. So dx equals, so dv equals dx. So v equals x. And now let's integrate by parts. So what do we have? X multiplied by sine of logarithm x minus, so this integral, yeah, and so x multiplied by this. And now let's simplify a little bit. So we received this integral, and again, integrating by parts. So why do we take u as a sine of logarithm x? Actually, this function is easier to differentiate. So actually, we need to integrate it. So and here we differentiate. It's more convenient. So what do we have here? So cosine of logarithm x. And here we have minus sine of logarithm x and divided by x. And for v, nothing changed. So minus, so this so let we open the brackets. So x cosine of logarithm x plus the next integral. So x, and again, now we will receive the integral. So we will receive the initial integrals, sine of logarithm x. So you see. So again, we transfer to equation. So equation with respect to this integral. So I just mark it as I for more convenience, for our convenience. So what do we have? I equals this minus x cosine of logarithm multiplied by x multiplied by cosine of logarithm x minus I. So I equals 1/2 of this expression plus c. Any questions about this exercise, about the whole lesson?
No questions.
Okay, so if no questions, so now let's finish. Yeah, Sophia, a question?
I have a question not about the today's lesson, but about individual home tasks. Where will they be uploaded?
Is it so? Is it not available for you now, for you yet?
No?
Okay, I will ask the lecturer to unlock it for you.
Okay, thank you.
More questions? Okay, so now have a nice day. Stay safe, and yeah. So just have a nice day. Enjoy your studying. Goodbye.
Goodbye.
Thank you,
Have a nice
goodbye.
day.
Goodbye.
Thank you for everything. Goodbye.
Goodbye.
That's it for